All right, guys, pretty exciting video here. Going to jump out of the theory a little bit and actually put this stuff to work. So what I want you to do is we had a data set called body fat. The reason I get on the treadmill every day is to try to eliminate that. So what I want you to do is go ahead and put this into R. And I'm going to do this, and while I'm doing it, I'm going to play you a song.
She said, don't you worry if I disappear. I told her I'm not really looking for another mistake. I called an old friend thinking that the trouble would wait, but then I jumped right in. A week later returned. I reckon she was only looking for a lover to burn, but I gave her my time for 2 or 3 nights. Then I put it on pause until the moment was right. I went away 4 months until our paths crossed again. She told me I was never looking for
All right, I hope you enjoyed that. Oh, I love going through my daughter's songs. Actually, again, don't tell anyone. I kind of like that. All right, where are we? Where we are is trying to keep Darbro from being bored to tears, putting up 10 videos a week. All right, gang, what I want to do here is I want to give an illustration on the effect of multicollinearity. And one of the first things that you'd want to do now that you've got that new that terminology on the that just rolls off your the tip of your tongue before conducting multiple regression with R. The first thing that I would want you to do is look at the following 2 things, and I would want you to look at a scatter plot matrix, and I'm going to show you how to do that. And I'd want you to look at a correlation matrix. Now, what we're going to be looking for here, the effect of multicollinearity is when we have 2 predictors that are highly correlated. So, what do we look for? Well, obviously in a scatter plot, we're going to look for relationships that exist. And in the correlation matrix, this is where things get a little confusing. It depends on the, get my hand out of the way there, that's kind of ugly. It depends on the sources that you look at. I've seen that any correlation between predictors greater than 0.8 is evidence of multicollinearity. I like to play it a little safer. Somewhere 0.50, 0.60. At the end of the day, multicollinearity, at least in my opinion, just creates a major threat to our assumption of independence. In fact, when we have multiple predictors, we can test independence by looking at the correlation across our predictors. So anyway, guys, I played the music. Sorry, and we got our data set up, and it's a data set that we've seen before. And when I first started using this data set, some videos ago, I noticed the multicollinearity when you do some just basic things, but I knew that this was going to be covered later on. So guys, anyway, let's see what happens. First thing I'd want to do is look at a scatter plot matrix, and it's actually kind of cool. You can get this very easily. Now, it's going to give you some stuff you don't want. What it'll do, it'll take every single variable in the data set, like subject. It'll give you a scatter plot of subject across triceps. Well, that's completely meaningless. And it'll also give you our dependent variable, which is body fat here. It'll give you relationships between the predictor and the predictors and the response variable. But what I typically want to look at the most is I want to look at the predictors. So if you'll watch my mouse, I want to look at this part right here, the inner part. These are the predictors, mid-arm, thigh, and triceps. and we get this correlation, or I'm sorry, scatter plot matrix. Now, when I look at this, the one I'm circling right here between thigh and mid-arm, I see no red flags. And, well, I'm sorry, that would be triceps and mid-arm. And the one I'm seeing right here, thigh and mid-arm, I'm seeing that those don't contain a lot of overlapping information either. When I look at this, I see a red flag. And I see a red flag between triceps and thigh, and it appears to me that these two variables are highly correlated. I mean, for obvious reasons. Well, you can see that from the scatter plot. And there's reason for me to suspect multicollinearity. And there's also reason for me to suspect that the addition of triceps and thigh into the model does more harm than good, because they're essentially measuring, or at least they're essentially kind of producing the same information. So let's go ahead and see if my the things I'm suspect on are actually true. Now again, in the correlation data, when we do correlation data, it's going to give all pairs, and sometimes you get things that aren't helpful here, like the correlation between subject and things. But you also do get this upper triangle here that's very, very helpful. So what I want to do is and I'm going to go over here and write this on the white sheet, if you will, and I want to look at the correlations, and I want to have this written down. So just let me get out of this and show you what I'm doing. What I'm doing here is just looking at the notation that we've done before. I'm looking at the correlation, across the predictors. And the way I wrote it down, the correlation between x1 and x2 was 0.92. Red flag, 0.48 between x1 and x3, and 0.09 between x2 and x3. Now again, x1 is tricep measure, x2 is thigh measure, and x3 is mid-arm measure. Now when I look at this, I have major issues. So let's, go to exclamation mark. There's something going on there. So there's a red flag, and since x1 seems to play a role in this high correlation, and equally does x2, what I'd like to do is examine what happens under different situations for x1 and x2 being in our model. So guys, at the end of the day, what I'd like to do is I'd like to look at our models and investigate the regression coefficients for B1 and B2 when I just have x1 in my model, when I have just x2 in my model, when I have x1 and x2 in my model, and when I have x1, x2, and x3 in my model. So I want to take a look at this, and this is something that's really easy to do with R. Okay. So because I'm going to be using, I could get my information very quickly, but I want to set up models for each one of these because, throughout this entire video, I'm going to be going back and forth to these models, so I want to save them. So it may not be clear why I'm doing so much work here. But the first thing I want to do is I want to create the linear model where I'm predicting body fat solely from triceps. And then I can look at the summary of model 1. And I can see that the estimate, well, there we go. The estimate for the regression coefficient, beta, would be 0.8572. Now I'm going to draw a line through the B2. Let me go back and just, I want everybody to be on board here because this is going to be something we're going to look at. So 0.8572 is the beta well, the coefficient estimate, if you will, when x1 is in the model, and of course beta 2 has no effect because it's not in the model. All right, what I'd like to do now is run a model 2. And, you know, you probably see what's coming here. I want to run body fat just on the thigh measure, because there's something going on with this x1, x2, this high correlation between triceps and thigh. Okay, so again, let's run our summary of our model. And when we just have x2 in the model, the beta coefficient for thigh is 0.857. Now what I'd like to do is I'd like to create another model, model number 3, and I want to run the linear model where we put or we predict body fat from both tricep and thigh. Okay, why didn't that work? Triceps. All right, gang. All right, so when we do that, notice that the tricep is 0.222. And the thigh is 0.659. Now what I'd like to do is I'd like to throw everything in the model, and we'll call this model 4. Right? Yeah. So now we're going to do the full-on effect, predicting body fat from triceps plus thigh plus mid-arm. So summary of model 4 gives me some wacky stuff. Now, the tricep measure, the estimate is now 4.334. And my thigh is negative 2.857. Now, going back over here, you know, that it doesn't take... you don't have to have a PhD in statistics to realize that's kind of wacky. And what is wacky, not only does the magnitude of the coefficients change significantly, and I don't mean statistically significant, we'll talk about that later, but notice that when we throw everything in the model, the effect of beta 2 drastically but changes because it changes from positive to negative. So if I'm interpreting this, I'm saying that controlling for a person's tricep and mid-arm, as the thigh increases 1 unit, the body fat decreases 0.286 units. Well, that is kind of wacky, and you know, we can just say that. Actually, we can say that these values varies significantly. And guys, again, I'm not talking about statistical significance just yet. When other variables are in the model. And you know, you know, I'm never going to sit here and tell you that I'm an expert on regression, but I feel like I know a little bit about it. In fact, I feel like I know quite a bit about it, actually. But, you know, you want some sort of stability in your regression coefficients when you add things. And, you know, we want, if we want to add something to our model, we want our error sum of squares to decrease significantly. Again, maybe not statistically significant, but we want to see the effects of our labor, right? So you know, there's something wacky going on here, and it all goes back, as you know, to to multicollinearity. So guys, a conclusion, what I can say is when predictor variables are highly correlated, which B1 and B2, or well, X1 and X2 are, the regression coefficient of any one predictor depends on which of the other are included or left out. So again, we add something, its impact, if you will, depends on what's either in there or what's not in there. So its inclusion is really doesn't represent the individual effect of the variable. It represents kind of a marginal effect of the variable. X1 and X2 are essentially giving us similar information. So because of that, with them being so highly correlated, when we put B1 into the model where B2's already there just isn't that much more information to be gained. There's not much more that we can do in terms of reducing the error sum of squares or increasing the regression sum of squares. Guys, hold on just a second. I have to, somebody's outside and I need to see what's going on. All right, guys. Sorry about that. I can't pause videos. I can maybe I'll edit that out, or maybe I actually should have played some music, shouldn't I? Guys, as we've talked about, when predictor variables are highly correlated, the regression coefficients depend on what's already there. And what I want to look at now is I want to look at the stability, or lack thereof, and the effect on the sum of squares. So let's write this down. I've kind of been. So we can say that when predictors are highly correlated, the stability of the reduction in the error sum of squares, so are highly correlated, the stability of the reduction in the error sum of squares must be viewed in the context of the other variables in the model. In college one time, I took a policy studies class. Yeah, I don't know why. I had to take something, and my PhD is in educational policy studies and evaluation, and I actually was in the part of that under the evaluation component, which was statistics, measurement, and evaluation, and they always wanted us to venture out, which I really didn't want to venture out because I like stats. But they made me take this policy studies class. And one thing that I remember my professor, if I live to be 600 years old, one thing I always remember my professor saying is, in terms of policy and setting policy, if two people always agree, then one of them isn't needed. And I can never think of multicollinearity, which is a statistical concept, which is a quantitative concept, without thinking of that statement. And if you think about it, if you serve on any committees, and if two people always agree, then there's that dependence. They're kind of dependent on one another. The independence, where they think independently of the other one. It's really meaningless to have them both, other than they get 2 votes instead of just 1. But in terms of bringing any new information to the table, there's no potential for that if 2 people tend to always agree. Now that comment will probably get me in trouble, but I really don't know why it should. But I think it's a great example, a non-quantitative example of what happens when things are related, when things are dependent, and in this case, highly correlated. Now, let's go quantitatively. So let's get out of policy studies and get back to statistics, which I like a lot better. Let's examine this. First of all, let's examine the sum of squares regression for our situation when just x1 is in. And guys, remember, this is what we did in model 1. So if we go back to R, and there's going to be a lot of this, so kind of bear with me. If we do ANOVA of model 1, we're going to get our ANOVA table. And the sum of squares regression when only triceps in there is 352.27. Now, I want you to compare that with sum of squares regression when we add x1 to the model, when x2 is already in there. Now, I want to investigate this this value, the sum of squares regression, when we have x2 already in the model, and look at the marginal effect of x1. Well, we can easily get that too by looking at, what was it, model 3, I believe, when we had just the 2. Yeah. And you can see there that we get, let's see, is that what I want? Okay, what do we have? x1 when x2 is already in the model. So actually I need my ANOVA for model. I messed up here, guys. So here we go. Yeah, that's exactly what I need. Now the sum of squares regression for okay, let me think this through. So this gives me the sum of squares for when x2 is in the model, and I want to see the difference when x1. So what I'm going to do here is take 381.97, and then I'm going to subtract out the sum of squares regression when we add x1 to the model, which would be right back here. So I need 352.27 plus 33.17. So, well, I got those backwards, but it would be 3.47. Obviously, the sum of squares regression is going to be bigger when we have both of the variables in the model. So, since x1 and x2 essentially contain the same information, adding x1 when x2 is in the model adds little to the variation that our model explains. So let's. So what I've tried to look at here is I've tried to look at the, first of all, just to summarize what I hope you've gotten out of this so far. I've tried to look at, first of all, what's the effect on the coefficients when we look under different situations. X1's in the model, x2 is in the model, x1, x2 is in the model, and so on and so forth. And I've also wanted you to think about the sum of squares regression and how there's little additional information when we add x1, in this case right here, when x2 is already in the model. And guys, again, that's just a straightforward effect of multicollinearity, having two variables, two predictor variables in our model that are highly correlated. So what I'd like to do next is I'd like to look at the effects on the standard errors. Now guys, at the end of the day, what do standard errors do for us for our regression coefficients? Well, I like to think of them most of all if we're examining our, let's say our regression estimate for beta 1, which is B1. And if we want to construct a 95% confidence interval, we add and subtract our t critical value, which corresponds to the confidence level that we're seeking, times the standard error for B1. So in other words, this standard error is critical in stabilizing the variability of our prediction from B1, or I'm sorry, for B1 for beta 1. So let's do like we did before, and I think this will be beneficial. Let's look at the standard errors for B1 and B2 under these situations. Okay? Now, if we go back to our first model, model 1, we can see that the standard error for triceps is 0.1288. I'll draw a line through the other entry because beta 2 wasn't in the model. If I come down to model 2, I'll see that the standard error for thigh is 0.1100. Now, what I think about, and when I see those two values, and go back over here, I really don't think much, but I want to see the marginal contribution. I want to see the change in these standard errors as we put information in our model, more information in our model. That's what we really get a look at. Now, when we come down to our two predictor model with triceps and thigh, we can see that our standard error increases, which is kind of weird, in both cases to 0.3034 and 0.2912. When we go all out with a three predictor model, we can see that the standard error for B1 is 3.016 and for thigh is 2.582. So kind of more wackiness, right? What this, again, gives us is just inflated variability. In a sense, and I'm not so sure this is the correct way of saying this, but it does our model harm instead of doing our model good. Adding more predictors, we would think that our model is going to get stouter. Now, there are a couple of places where the model actually does get a little bit better. And if we look at the effects on the mean square regression, well, I tell you what, let's look at the mean square error term because it should decrease. So if we look at the effect of the mean square error in our ANOVA under the different conditions, what are we going to get here? Well, I think we pulled up ANOVA of model 1 somewhere. Yeah. So the mean square error was 7.95. And really, yeah, let's just go ahead and look at, I haven't done a ANOVA Model 2, have I? Yeah, I did. So our mean square was 6.30, mean square error when we had, is that the right one? Yeah. Now let's see what happens to both of those when we put two predictor model. And we can see that this decreased to 6.47. You know, concentrating on B1. And then we put everything in the model. I don't think I've done that, have I? So let's run an ANOVA for the full-on. And we can see that our mean square error dropped to 6.15. So again, just focusing on X1, we can see that adding X2 did decrease the mean square error as we add more predictors, even though they're correlated. And another thing that we can say is that even the fitted values don't lose much when we have multicollinearity, but the impact on the coefficients and the impact on the error sum of squares and regression sum of squares is clearly quite substantial. Now, I don't know how much time I got left. There's something else I really want to show you, and I don't know whether to stop this video. I'll tell you what. Let's just keep going. Let's examine the effects on our test for adding or eliminating coefficients. Okay, now let's say number one, first thing we'd like to do is we'd like to test two things. First of all, I'd like to test beta 1 equal to 0, and I'd also like to conduct a separate test for beta 2 equals 0. This is actually kind of good that you know, we pose that at this stage of 6500. You know, what would we do? Well, we're conducting two tests. So inflating what we call the family-wise type 1 error rate. Is probable. So what we need to do is we need to control for that. And one way we could do is just a very simple correction process called the Bonferroni correction process. Bonferroni, if I remember correctly, Bonferroni, what it does is it takes the p-value that you get and then you multiply that by the number of comparisons that you're making. So it bumps up the p-value because it realizes that the alpha you're testing at, when you conduct more pairwise comparisons, your alpha will become inflated. And since we're making two comparisons here, bumping the alpha level to 0.025 So we're just making it more stringent on our p-value. Okay. So we're tightening up the reins, if you will. So if we get into R, and what we want to do is we want to look at our sampling distribution for T with degrees of freedom. In this case, would be what? N minus K. So our degrees of freedom would be what? 17, since we have 3 predictors. And we want to find these values here that essentially finds 97.5%, because what we want to do is we want to have 2.5% divided by 2 in this tail, and 2.5% divided by in this tail. So what we could do here in R is we could go QT 0.025 divided by 2 and our degrees of freedom. So let's bump over there and get that. So 0.025 divided by 2. Degrees of freedom 17. So what we get is we get negative 2.46. Okay, so that's that will represent this value, and for obvious reasons, this will be positive 2.46. So if our test statistic, actually the absolute value of the test statistic for our beta coefficient estimates, beta 1, beta 2, beta 3, is greater than 2.46, we reject H sub O. And again, what are we testing? We're testing these. Well, guys, we can go back and get our values. We ran that, I think, didn't we? For the full-on model? Yeah, right here. So the test statistic for triceps was 1.437. And the test statistic for thigh was negative 1.106. Now, the thing to keep in mind here is neither of these in absolute value form is greater than 2.46. So we fail to reject the hose, if you will. So we fail to reject H sub O beta 1 equals 0 and H sub O beta 2 equals 0. Okay? And that's going to be the easy way of doing that is just look at the p-values, and obviously neither one of those is less than 0.05. Now the only reason I do that is for this next thing that I want to look at. I haven't run the calculations on this yet, so it's going to probably be a little clumsy. But I want to look at this in the context of this extra sum of squares, which has kind of been the overarching title of the recent videos, and test as we've seen before. All right, so at least 1 is not equal to 0. And guys, so essentially what we're doing is we're examining the full-on effect of the model, but at the end of the day, we want to look at the effect of adding x1 and x2 and x3 is already in the model. Now, something you should know, and I think if you've been really paying attention to the videos, which I hope you have, we know that the mean square regression will look at x1, x2, and x3 is in the model. And, of course, our mean square error term is the full effect. Now, this is going to break down to the sum of squares regression for adding x1 and x2 to the model when x3 is already in it, divided by its degrees of freedom. So we're adding two terms, so degrees of freedom will be 2. And we want this over the error sum of squares for the full on. And of course this is going to be n minus 4. Right? N minus k minus 1, k predictors are 3. Yeah. All right, so let's go get that. You know, we have a data set of 20, so that's going to be obvious. And the sum squares error is going to be really easy to find. If I can find the ANOVA for everything, so that looks like it's going to be 98.40. All right. Now, so the denominator of the numerator is going to be 2, so that's what I'm doing there. Now, the next thing we've got to do is we've got to find the sum squares regression of x1 and x2 added to the model when x3 is already in the model. So we're going to have to run an extra model here with x3 only in the model. So let's name it what you would think we would. And I want to run body fat over mid-arm. And I want to run ANOVA of model 5. And I want to get take a look at the sum of squares regression, which is 10.05. Now I want to look at the ANOVA for model so what do I want here? Let's see, I want to add x1 and x2 to this. So I just want the full-on model, don't I? I want model 4. Now, for the sum squares regression, we can see that we have 352.27 plus 33.17 plus 11.55. And I want to subtract out the sum of squares regression, 10.05. And I get 386.94. All right, gang, let's go back over here. I'm going to grab the calculator and see what we get here. So it looks like that the mean square regression is going to be for adding x1, x2, and x3's in is going to be 386.94 divided by 2, right? Yeah. So that's going to be 193.47. So that's a mean square regression, again, adding x1, x2, and x3's in the model. And then I want to take 98.40 divided by 16, and I get 6.15. Now that's going to be pretty big value. Divided by 6.15, and I get 31.46. Does that seem reasonable? Now, I don't, I don't think we need R to tell us that's going to be statistically significant, but looking at the F distribution of degrees of freedom 2, 16, I'm betting, what did we say, 31.46, is going to have very, very, very little room out there. And what we can do here is we can go 1 minus PF of 31.46, comma 2, comma 16. I'll tell you what, let's do that just for the heck of it. So 1 minus PF 31.46, comma 2, comma 16. And yeah, very small. So we get statistical significance at the 0.001 level. Now guys, remember, what did we test? Essentially this, right? Well, if you guys could see what I was writing, it'd probably help. So we have just rejected the crap out of this null hypothesis, concluding that the alternative is the most reasonable and acceptable statement. But guys, this is a complete contradiction. Contradiction. Okay. Guys, I promise you I can spell, I just can't see. A complete contradiction of what we got when we tested the coefficients individually. And the reason is we thought we were testing them individually back here when we ran the coefficient output right here. We thought we were testing those individually. But again, it goes back to the policy studies example. If two people always provide the same information, then one of them isn't needed in terms of, you know, making productive contributions to the overall picture. So, guys, again, we think that we're doing individual contributions, but because triceps and thigh are so highly correlated, there's actually that marginal contribution. Now, again, the reason for the contradiction, each test of the coefficients turns out to be a marginal test. And you can really see that if we examined the following sum of squares regression. Let's look at adding x2 and x1 is already in the model. And let's look at adding x1 in the model when x2 is already in there. And when we do that, and might as well just go ahead and do it, we can come back and look at the sum of squares regression. See, that would be model 2, right? We had, yeah, right here. Well, guys, I need to go way back here someplace. Okay, we need to find ANOVA model 2. So when x2 is in our model, well, let's do x1 first. Okay, so when x1 was in our model, our sum of squares was 352.27. And when I added x2 to that model, and that should be model 3, if we run an ANOVA model 3, yeah, well, thought we did. This is the 2 predictor model. You can see that the contribution was 33.17, relatively small. And when we run the model the other way, we also get a small contribution to the sum of squares for regression. So anyway, guys, at the end of the day, what can we say? In the way I look at this, multicollinearity is a violation of independence. We have predictors that are highly correlated and highly related. So in the body fat example with triceps, thigh, and mid-arm, we see the triceps and thigh are highly correlated. They are essentially providing the same information. And once one is in the model, the addition of the other one does little to decrease the error sum of squares or increase the sum of squares for the model or sum of squares for regression. So gang, that's all I got. I didn't do the calculations, but both of these were small contributions. All right, gang, smiley face. This is the end of the video. Bad news is, or good news, however you want to look at it, is that it's going to be time for a homework assignment. I'm working on that. I'm trying to get problems that are fair yet challenging, and also that make a point. And you know what? The E word is coming up too. It's going to be kind of a natural place in this semester to insert examination. So, guys, take care.